In this class, we're going to review all the key concepts for solving exponentials and logarithms. Enjoy. Okay, let's do one on exponentials and logarithms. Okay. Cool. So there's a fair bit in there. Do you want me to do a review of like top to bottom of that stuff, or you want to practice stuff from within exponentials and logarithms? What do we think? Practice, or do you need like a review? Top to bottom. Yeah, sure. Okay, let's have a look. Functions, relations, exponentials, logarithms. Cool. So one of the first things you'll need to be able to do for exponentials and logarithms is understand your index laws quite well. This will allow you to solve quite complicated exponentials simply because you're now dealing with different powers, essentially. Index laws, very briefly, as follows. They all revolve around when you have two things with the same base. In particular, if you're multiplying, you add the powers. Doesn't matter if they're fractions or not. If you're dividing, you subtract the powers. Doesn't matter, again, if they're fractions or not. If they are, if you have cascaded powers, so in this case we have power of m and then on top of that a power of n, then that's when you multiply the powers together. If you have a set of like multiplications or divisions that are all raised to the same power, then that power can be distributed into both of those products or both of those divisors. That's basic index laws. You can use those to solve all sorts of questions from that particular chapter. A few further identities that are worth understanding, especially when it comes to solving exponential functions, is whenever you have power of 0, that thing equals 1. Doesn't really matter what the base is at that point. Negative indexes are just fractions, so any b to the power of negative m is the same thing as 1 divided by b to the same power of m, but this time it's not a negative anymore. And one last thing you'll need to know is that any root can be rewritten as an equivalent fractional index. So if you have a fractional index like this, the way it works is the numerator is your power of that base, and the denominator is the number of root. So if I had x to the power of a half, that is power of 1 on the beta, or on the x, and it's the square root, so because of that division of 2. Those are all sorts of things you can use to solve things like that. Okay, next up, solving exponentials. So there's 3 main techniques that you can use for solving exponentials. You can do so by equating exponents, quadratic solutions, or using logarithms. So we're going to look at an example of all of those. If I need to slow down at any point, just, sing out. But okay, equating exponents. We follow these 3 steps here. The whole idea is that all else being equal, if two sides of your equation look more or less the same, then you could ignore the vast majority of it and only focus on the bits that are different. And we use this principle in the equating exponents approach by starting to rearrange all the terms in here to have the same base. So 27, if you were to rewrite that as a base and power, is 3 to the power of 3. And so when you're looking at both sides of this equation, you can even just visually observe that if the bases are the same, then the only thing that matters at this point are the powers. So in this case, x would have to equal 3, then you would have 3 cubed equals 3 cubed. You can almost do that by observation. If it gets a bit harder, you might have to actually solve something. So in this case, 25 is just 5 squared. You use your index laws, so what we just covered before. When you have power and then power again, that's a multiplication. So 2 times negative x gives you negative 2x. 2 times 2 gives you 4. Bases are the same, and so you could ignore everything else and just focus on those exponents, solving for x from there. Quadratic solution. So when you have multiple exponentials in the same equation, it's pretty likely that you can solve it with a quadratic solution. What that means is you start again by trying to get everything into same base where possible. In this case, when you have multiple exponentials, the only thing that you actually care about getting same base are the exponentials themselves. In this case, it's already been done. Both of these have a base of 3. But if this one had a base of 9, for example, then you could rewrite that as 3 squared. So 3 to the power of 2x, should you wish. But in this case, we don't need to do anything like that because it's already same base. From there, you do a substitution. That means you look at your exponential equations, the exponential terms in them, and you pick the common exponential between both. In this case, the common factor there is going to be 3 to the power of x. And you can see that if you do a bit of rearranging here. If you take that power of 2 off of this, you can see we've got this common 3 to the x in both. So if we replace that with some letter, I'll just use a. Now it looks like a quadratic. And so you just treat it like you would for any quadratic. You could factorize, you could complete the square, you could quadratic formula, whatever you like to do to solve quadratics. That'll give you 2 solutions to a anyway. But reminder that a is 3 to the power of x. So instead of saying a equals those 2 things, you now say 3 to the power of x equals those 2 solutions. Only one of them is going to have an actual solution because, well, maybe I'll let someone else tell me. Any ideas why 3 to the power of x should never equal -9?
You can't have a negative number when you put an exponent on top.
Yeah, basically. Well, at least in this case. So if you think about the possibilities for x, you can choose positive numbers, negative numbers, 0. Those are the main things that will cause any different behaviors. If you imagine choosing a positive x, the number's just going to get bigger. For example, 3 squared is 9, right? If you just keep doing a bigger power, it gets bigger and bigger, not even close to negative. If you choose a negative index, then what you're choosing to do is make this into a fraction now. 1 divided by 3, 1 divided by 9, 1 divided by 27. It never actually goes negative, though. It only gets closer and closer to 0. And then potentially the last possibility would be to sub in 0, but in that case you just get 1. So nothing actually quite makes it negative. Now, if you did have negative 3 to the power of x, and what I mean by that is a negative on the outside of the exponential, which I'll start writing in the handwritten bit, then this could have a solution, because now you have negative 3 to the x equals negative 3 squared. Now it's possible to have a negative there, but only because the exponential itself was already negative. Is it clear the nuance there? Okay. As for when to use a quadratic solution, again, kind of like what I mentioned before, if you have multiple exponentials in there, then it's pretty likely you'll have to use a quadratic solution. Other things you could look out for are these descending powers of x. So you can see a 2x, a 1x, and a 0x. That's kind of like how quadratics works. And the other thing would be if you have coefficients on your exponentials. So if you have like a 6 times or a 2 times. And the reason why around there is because when you have coefficients, equating exponents doesn't quite work out as well as it normally should. But really the main thing is just, do I have multiple exponentials? If so, try and make a quadratic out of it. Yeah. Last bit would be logarithmic solutions. This always works if you have just a single exponential to worry about. The gist of what you do here is you just convert to log. So easiest way I know to do this is to start by getting the exponential specifically on its own. So in this case, it would mean dividing both sides by 5. And then lastly, once you have that exponential on its own, you just flip the terms around as required by the logarithm conversion, which I will show you in a second. Okay. So that's how this one works here. So if you have some exponential y equals a to the power of x, the equivalent logarithm would be to put whatever the equal sign goes in the brackets of the logarithm, the base of the exponential is the base of the logarithm, and then the power of the exponential is the equal sign for the log. That's the shorthand conversion of things. If you find that hard to memorize, one other thing you could potentially do, and you will need to know this skill anyway, is to, quote, apply a logarithm to both sides of your equation. Now, what that means is, if you imagine, in the handwritten bit now, if you imagine y equals a to the power of x, just like how you can subtract both sides, how you can square root both sides, anything like that, you can also apply a operator to both sides. And the way that works in this case anyway is applying a logarithm to both sides. So I could write log a of y equals log a of a to the power of x. So basically wrapping both sides of my equation with a log a. Now from here you could use the so-called log laws to rearrange this. We are deviating a bit from the initial lesson, but that's okay. Let me just show you the log laws ahead of time. Okay, so back on the screen share, the key one of interest is the power law here, which says that if the brackets of your logarithm have a power, and that means the entire bracket of your logarithm has a power, then you can bring that power out the front of the logarithm. So the way we apply that in the handwritten section is, you see we have a base of a bracket with a to the power of x. So the entire bracket is to the power of x, and for that reason, using our log law, we can bring that x out the front. Log a y equals x log a. Getting closer. The final thing we have to worry about is this logarithm on that side, log a of a. Now, one of the key things about a logarithm is that if you have same base and bracket that I'm pointing to in the screen share version, if you have this identity 1 here, this same base and bracket, it will always equal 1 no matter what. Now, the proof of this is somewhat cyclical in the sense that you prove it by converting to exponential. We'll ignore that nuance there for a moment. Point being the fact that whenever you have base and bracket the same, that will always equal 1. So if we go back to the handwritten section, we're going to have log a of y is equal to x, and sure enough, things are being moved over the way that we expect them to be moved over. The equal sign goes in here, bases stay the same, exponent comes out front. So, all things considered, if you forget how to convert, usually I've found that most students don't find the log laws to be particularly hard. It's more so remembering how to flip things around at the beginning. So there's that. And the way that we handle, well, the way that we take advantage of that is when we have an unknown in the power, so back to the screen share, when the unknown is in the power, like in the exponential example, converting to a logarithm brings power from the power, brings the x from the power to the to the line where you can get it on its own. And that's the gist of it. Only thing I'll mention there is the notation there. ln stands for natural logarithm, and the natural logarithm is just something that it's a logarithm that has a base of e, which is what we expect it to have, base of e here. Just 1 second while I take a sip of water. Okay, so that's the 3 key ways that we can solve exponentials, at least exponential equations. One of the things we also have to look at is how to solve exponential inequalities. A little bit different. Thankfully, we did just have a look at the method by which we can do this. So, as follows, you'll have some sort of exponential like this. So in this case, 0.4 to the power of x less than or equal to 0.3. My personal recommendation is to solve it the same way that I've shown you how to convert between exponential and logarithm. The reason why I propose that you do it that way is because you can't necessarily just swap the terms around and be okay with it. because of this inequality. When you have an inequality, it matters what side you put things on each side of the equation. If you look back to the handwritten notes, you'll actually notice that when I converted from exponential to logarithm, the how to say it, the terms haven't necessarily stayed on the side that you expect them to. Normally when you give an answer, you say x equals something or y equals something. In the process of converting from exponential to logarithm, we've actually flipped the order in which terms are being written, which is fine in an equation because it doesn't matter what you put on either side for the equal sign. But if there's suddenly an inequality here, you're going to have some issues. And so my recommendation is do this, because then it's super obvious what side things should be on. Or if you do try to change the side, you can compensate for that. But okay, so we're going to do exactly that. That's what the next step is going to be, applying the logarithm to both sides. Now specifically, you're going to choose the base of your logarithm to be the same as the base of the exponential. So back to the screen share, you've got a base of 0.4 that you're working with. So we're going to apply a base of 0.4 to either side of our logarithm. One thing that's of interest is that if you use a base between 0 and 1, you have to flip the inequality. So it was a less than or equal to sign. Now it's a greater than or equal to sign. That's one downside of having to do it this way. You have to make sure that you, if you're going to use these strange-based logarithms, you have to remember to flip that sign. I will say it is the lesser of two evils, as you'll soon see. But anyway, so after having flipped the direction of the inequality, we're just going to do the exact same thing I mentioned before, which is going from here to here. So you're going to have this is a power, and so it comes out the front using that power law, and then same base and bracket means that this cancels down to just 1, leaving you with x greater than or equal to log 0.4 of 0.3. You can choose a different base if you want. If you're looking at this inequality and you're thinking, no, I don't want to memorize flipping that around if I use base between 0 and 1, then by all means, you can use a different base if you want, but I'll show you one of the downfalls that you now run into. In this case, I'm choosing a base of e on both sides. You'll notice things are cool so far. The inequalities haven't changed directions just yet. We're still following the same procedure as before, bringing the power down the front, and then the next natural thing is to divide by natural log of 0.4. Here's the issue. Is log of 0.4 a negative number or a positive number? Because when you divide or multiply on an inequality, any negatives will cause it to flip. I don't know about you guys, but I don't know at a glance if my logarithm is positive or negative. It's pretty tough. I'm sure you could at some point memorize it. I haven't yet. So if you want to go down this way, you do have to figure out whether or not this is positive or negative.
Chris,
Yeah, what's up?
so you know that in front of the X it says ion, or I'm not sure if that's ion,
Yeah,
and
Ellen.
it has e to the power of y at the bottom of the page. So what's these things are?
What are they? Okay,
Yeah.
yeah, so this ln stands for natural logarithm. It's the same as saying log e of something. The thing about e, the reason why that's bold is because that's a special number in math, kind of like how pi is a special number in math. And so if we look at somewhere in the definition, let's see, do they have a definition for it? Surely. Yeah, there you go. It's called Euler's number. That's actually how you pronounce that, I believe. And it's got some math background as to where that number came from. The only thing you really need to know is that it's approximately 2.7. So you can see as the numbers converge closer and closer, you can see it's approximately 2.7. Just like how pi is approximately 3.14. That's really all you need to know about that. Does that clarify what's going on there?
Yep. Thank you.
No worries. Okay, so back to the problem statement, which was, is natural log of 0.4 a negative or a positive? Well, there is a way to find out, and that is to convert to an equivalent exponential. So you have your natural log of 0.4. That's the thing you care about. And so we're just going to slightly deviate from the initial question and then go on our own little tangent to say, okay, I don't know what natural log of 0.4 is equal to. Let's say it's equal to something called y. What is that y value? Well, you're not going to get an exact value necessarily, but if you go through that conversion formula that I detailed in the beginning, which is just swapping the terms around, something you'll have to just remember, you'll get e to the power of y equals 0.4. Now from there, you just sort of go through the guess and check method that I mentioned at the beginning when it came to, what was the example? When it came to this, right? The reason why this has no solutions. You guess some positives, you guess some negatives, you guess some, yeah, anything like that really. And you figure out what would y be closest to. Is it a negative, is it a positive? Well, if e is approximately 2.7, then any positive power would cause it to just become bigger, right? 2.7 squared is going to be something slightly bigger than 4. And as the powers get bigger, it's just going to get a bigger number. So we're getting away from 0.4, which is bad. However, if you choose negatives, now you're suddenly doing 1 divided by 2.7. 1 divided by 2.7 squared. So if we just do some calculator bashing on the handwritten bit, I'll start showing you some possibilities. Or I'll even just use negatives actually. So e to the negative 1, well, it's actually already too small. Negative 1 was a bit too drastic. So let's say e to the negative, I don't know, 0.1. That's approximately 0.9. If you do e to the negative 0.2, get a bit smaller. E to the negative 0.5, you get a bit smaller. Point being, if you go negative enough, you will hit 0.4, and then the fact that it's negative y, does mean that our logarithm has to be negative, because if you go back to the screen share, solving for y means solving for that logarithm. So if you know it's negative, that you come back here, divide both sides by natural log of 0.4, and you end up having to flip the inequality anyway, because you're dividing by a negative. So not only that, but you also have a bit of a nastier solution, where you've now got 2 logarithms on one equation. Was that clear enough? Do I need to clarify anything that was going on there?
Chris,
Mhm.
when we were doing like the first method of the of solving the inequality,
Oh, yeah?
not yeah, like the logarithmic solution.
Yep.
I kind of lost you where we had went from x times log 0.4 base 0.4 of 0.4, and then like why did like the left side of the log just like vanish?
Yeah, no, fair enough. That is from this identity that we covered a little bit ago, which was whenever you have same base and bracket, so a and a or 0.4 and 0.4, that's always equal to 1, no matter what. And so anything, so x multiplied by 1 is just x. Is that a bit clearer?
Yeah, thanks.
Nice. Yeah, and feel free to hop off mute as I'm talking. I'm not offended if you want me to slow down at some point. But yeah, so those are the 2 possible ways of going about it. I think this is the lesser of 2 evils, but if you like doing this, then I'm not going to stop you. Okay, that is solving exponentials. Next up is graphing exponentials. Cool. So the transformed state of an exponential is going to look something like this. Hopefully not nearly as bad as that. I've just shown you all the possible transformation factors there. You've got dilation factors A and D. You've got translation factors H and C. And one thing that's not quite present there are the reflection terms. A negative out here would be a reflection in the x. A negative on this x would be a reflection in the y. But we'll see that. First things first, without any transformations, your exponential will look something like this. Most people tend not to have an issue with that because a lot of things, well, maybe not a lot of things, but enough things in real life do have exponential curves to them. If you think of things like investing, if you have compounding interest on your bank account, ideally your bank account would look something like this and not like well, I'll just leave that there then. Point being, this occurs in nature, so it's usually not so bad to think about what an exponential curve might look like. The reason why it looks like this is because, so this is just the power 2 to the power of x. If you were to just test some possible x values, you would notice that as x gets larger, the power gets larger, and your y values are exponentially getting bigger. So they're doubling every single time you increment your power. Whereas if you choose negative values of x, again, that comes back to where you have fractions involved. So 2 to the negative 1 is 1 over 2. 2 to the negative 2 is 1 over 4. We're getting closer and closer to 0. That's why as you get more and more negative, you asymptotically, so never actually, approach 0. That's that. If you get a larger base, so if you compare 2 to the power of x to 10 to the power of x, well, the 10 to the power of x is just going to be a more dramatic version of that. If your base gets larger, it's just more dramatic, because now you've got 10 to the power of 1, 10 to the power of 2, right? It's going to increase way faster than 2 to the power of x will. Because, well, if you compare the two x values of x equals 2, 10 squared is 100, and 2 squared is 4. So a very much dramatic increase. But it also comes at the cost of a, well, I say cost, it comes at the side effect of a dramatic decrease on the negative side, because now you got 1 divided by 100 versus 1 divided by 4. One thing that's also interesting to note is that this is the first graph that now has different behaviors beyond just the typical transformation terms. The base of your exponential actually also ends up being a kind of reflection term. When your base is between 0 and 1, you actually observe an apparent reflection in the y-axis. So normally it was pointing in this direction, now it's pointing in the opposite direction. Hopefully zooming out isn't too bad for the screens you have. Basically, you imagine the green line has been flipped. The reason why it behaves like this, again, can be figured out by testing some x values. So testing some x values, you'll see that as x gets larger, the y values shrink more, because using your index laws, these powers get distributed to the top and bottom of your fraction. So if you imagine like f of 2, for example, that is just 1 squared divided by 2 squared. So 1 divided by 4, so on and so forth. So you see that it's flipped essentially. Positive x values are now tending closer to 0, and negative x values are flipping our fractions to integers. So instead of being 1 divided by 2, when you raise that to a power negative 1, you flip that. And that's giving you the 2, the 4, the 8, and so on. So your negative x values are shooting off to the positive. Once again, if you have different bases, you'll see that effect worse. So essentially, as your base gets closer to 0, the effect is magnified. So you're getting the same effect as if I had said base of 10. Anything to clarify, please let me know. Otherwise, I'll continue on. Okay, dilation factors. These do work basically the same way that they've always worked, where this term out the front is a dilation along the y, or from the x. Those mean the same thing, basically meaning stretching upwards. And this d term is stretching horizontally. That is termed a dilation along the x or from the y. That's what horizontal dilations are like. You'll notice that the effect is significantly less than changing the base, and that's simply because multiplying something by a flat value has a dramatically less importance than tripling every x, or if I'd replace this with 10, for example. because just tripling the number after you've made it exponential is a lot less of an impact than if you had put it in the base instead. Yeah, okay, here's a version of D. Just be aware that dilations in the x direction appear as divisions, so bigger denominator actually makes it further along the x, and bigger, I guess you can call that numerator if you want, that will cause it to shoot up. Reflections, so the weird thing about exponentials is now when you have your reflection terms, you also have to marry that up with the fact that base can also act as a reflection term. So basic version, base is greater than 1. Your graph is going to look like this. If you put a negative sign, that is a reflect in the x, and so it's going to start pointing down. But if your base is between 0 and 1, normally it would look like this. And so a reflection in the x is going to be this bottom bit here. Reflection in the y, that's when you have a negative sign on the x specifically. So again, 2 to the power of x normally points to the right. Reflecting in the y now causes it to point to the left. Whereas if your base is between 0 and 1, it's going to point to the left normally, and the reflection will now cause it to point to the right. These images can be a bit confusing. Do I need to explain what's going on in any more detail? Okay. Translations. So the only translation that really matters for exponentials is the vertical translation. As you might notice, the horizontal translation isn't really doing a whole lot different to the graph. It is shifting it to the right, or in this case, to the left. That does work the same way as quadratics, by the way, as any other function. Whenever you have x minus h, you shift right by h. Whenever you have x plus h, you shift left by h. But as far as changing how you actually draw the graph, it doesn't really do a whole lot, at least not by hand anyway, because all it really does is change what you label your y-intercept to be, or your x, depending on which direction it's pointing. Vertical translations matter a fair bit more, because when you're drawing this by hand, you are required to label your asymptote. So if I have a +1 out the front, I'm shifting up by 1, and that's also going to bring the asymptote up with it as well. Normally there's an asymptote at y equals 0. When you shift up by 1, you now have an asymptote at y equals 1. As for negative, so if you shift down by 1, so function minus 1, your asymptote is going to go down by 1. So y equals -1. Okay, the things you need to know to sketch by hand. So first up, asymptote is always going to be given by the c value. That's pretty important. That is a key feature. From there, as long as you know your x-intercept and your y-intercept, you can draw your graph through those points, and I think as long as you know x and y, there shouldn't be a way to mess up the shape of the graph. Yeah, that sounds about right. So solving x and y-intercepts is the same way that you would always do it, at least initially, which is y equals 0 for the x equals 0 for the y. Now, the actual nuances behind that is a bit different, because when you set y equals 0 for this is an exponential, and so you treat it like solving an exponential equation. If you remember the 3 key ways that we have for solving exponentials, the one that we use often is going to be this logarithmic solution, which means getting the exponential on its own and then transforming to a logarithm, which is what we're going to do here. So this is our exponential thing. It's got this c value, get rid of it. It's got this a value, get rid of it. Exponential is now on its own. We've got some base, we've got some power. From there, you'll have to memorize or otherwise know how to flip to logarithm. That's going to free the x value, or at least get it closer to being freed. All you have to do from here is multiply by that and add that. And this whole thing will be your x. Now, the thing of interest here is that not all logarithms have an x-intercept. These ones don't. These ones don't. Only this one does. And that's because most I meant to say exponentials, if I didn't say exponentials. Most exponentials don't actually cut the x-axis. They're asymptotic at that spot, or even further above. So it's pretty rare for it to have one to begin with. One thing that you'll notice if you do try to solve one that doesn't exist is that you'll get a negative in your logarithm. Now, it kind of works the same way as square roots does, in the sense that if you have a negative in your logarithm, it's specifically it's non-real, I think. Is that what it is? Yeah, not real. For anyone doing spec, that might matter, saying that it's not real for negative versus being undefined for 0. For us, we don't really care if we're doing methods. Basic point is, don't have a negative, don't have a 0 in your logarithm, and if you do, you know that your solution does not exist. So to avoid that, if you're already quite familiar with how all these shapes sort of play together with all their transformation factors, then you can know ahead of time, do I even have to bother trying to find an x? Like if you know 2 to the power of x plus 1 is shooting off and to the right after it's been shifted up by 1, then you don't even bother looking for your x, because you know it's going to go up and to the right. So this is one of the advantages of being familiar with the shape, rather than just trying to brute force all the key features out of it. That's x. Y-intercept is significantly easier. You just sub in x equals 0, and oftentimes it's literally just that simple. No further rearranging required a lot of the time. Okay, as for how we sketch, well, here's the framework. We'll look at it line by line. So the way we handle all functions is we start by trying to get them into their general form, or you could consider it their transformed state. The reason why is because we want to understand what all the key features are. Like, are they translations? Are they dilations? What kind of stuff are we dealing with? So, a couple of things we have to do. One is to distribute this -3 through both sides. So we're going to have -3 on this, and then -3 on this to make it +1. Then from there, the only other thing that's left that you could look at is to take this common factor of 2 off of the x. That way you know for certain that your horizontal translation is 3 to the right. That part in particular doesn't really matter much for sketching it by hand. It'll matter a bit more if you're doing an investigation sac, because investigation sacs typically will ask, hey, here's this term in my whatever function, what does it do? If I make it bigger, what happens? If I make it smaller, what happens? So being able to do this is still worthwhile, understanding that you should do this in most cases. It just tends not to be super important for exponentials. Anyway, asymptote, y equals c, that's your c, whatever the vertical translation is. So this +1 tells us that we have an asymptote at y equals 1. You wouldn't have seen that if you didn't distribute this negative through. So it's a pretty important thing to make it look like the proper general form. From there, we're going to identify some reflection terms. So we care about base. Base will impact what it starts out like, and we care about negatives on the y and the x. In this case, it's only a negative on the y, and so that's going to flip it downwards. The normal exponential e is a base greater than 1. It's 2.7, and so it should normally go from point up to the top right. Now it's going to go down to bottom right because we're flipping downwards because of that negative sign. So being able to draw a quick graph like that is nice because it tells you, okay, I do actually need to find an x-intercept. Whereas if it was pointing upwards, you wouldn't bother. So now that we know we need to find it, let's start by finding some intercepts. So first things first, x-axis intercept, y equals 0. Sub in y equals 0, get the exponential on its own, and convert to logarithm. This is what we were talking about over here. The slightly more complicated example. So it would be subtracting 1, dividing by -3. That gets you the third over here. And then because you've now got exponential on its own, you can flip that to a logarithm. From there, it's just rearranging for x at that point. It's not uncommon for your values to have like full logarithms in their solution. I've only written the approximate thing there just in case your question asks you to go to 2 decimal places. If it does, it means it was a CAS question, so don't feel like you have to figure that out by hand. Okay, that's that. Y-axis intercept, x equals 0. Again, it's about as simple as it appears. You replace that x equals 0, and in a single line, you can't really do a whole lot different. Pretty unlikely for you to have endpoints. Usually you draw this over all real numbers, and then you sketch. So we know the y, we know the x, we just draw our curve to cut through those things. Now, one thing that you will have to understand how to do is to know, is this a positive? Is this a positive? Is this a negative? Is it a negative? My recommendation is to focus your efforts on the exponential rather than the logarithm. We already saw how much effort that logarithm took to try and figure out if it was positive or negative. That was when we were looking at the inequality over here. Remember all the converting we had to do there to figure that out? So rather than go through that to try and solve this, it's a little bit easier to go for the exponential instead, because it's already in that exponential form. So what do? Well, we know that E is approximately 2.7. This is something that actually now starts to matter to know what E is approximately. When you have a power of -6, that's the same thing as saying 1 divided by e to the power of 6. Or in this case, it'd be -3 divided by e to the power of 6. So e being 2.7 with a positive index, when it's in its denominator anyway, makes that a pretty large denominator. So even if you just round this to like 2, right, you got 2 to the power of 6. Fairly big denominator. Multiplying it by -3 isn't going to do a whole lot. It's going to make it negative, firstly, but the multiplication of 3 isn't really going to do a whole lot as far as the actual number is concerned. So when you have really small negative number plus 1, it's going to be positive. So you basically do that. You look at the relative impact of both terms, you compare which one should be dominant, and from there you can tell whether it's positive or negative. Once you consider whether this is positive or not, it doesn't actually matter what this is or having to solve it. There's only one way to draw the graph. If you cut through here, there's no way it can go back on itself to then cut through on a negative y, or a negative x rather. It has to keep going this way, and so it has to be positive. That can be tough. Did that make sense? Do I need to explain that anymore? Okay. If for whatever reason you have a restriction on your domain, then you handle it like any other function. You sub in the values into your original function, and you get the corresponding y values at that spot. Again, you're likely to have some weird nonsense as part of your answer. As far as cutting the graph off at those particular points, just be mindful of what dots you use. If it's square brackets, you use full circles, so square bracket on that, full circle, open circle for rounded brackets. Same as any other function. All right, that is that. That is a lot on all the exponential side of things, and a bit on logarithms. Got about 15 minutes left of the class. Do we want to practice any questions, or should we just round this off with more logarithm theory? I'll leave that up to you guys. Okay, let's do some practice. We covered a fair bit. We're not going to be able to practice all of it. Do you have any particular things you want to have a look at from within that? I've got the chapter list up on the screen share.
We do 5D.
5D? Yeah, okay. 5D, let's see. What are the interesting things in here? Evaluating logarithms, that's going to be converting to exponential. Got some log law stuff. Yeah. Lots of log law stuff there. Cool. Alright, let's try at least do one of question 1. We didn't really talk exactly how you evaluate a logarithm. It is just converting to exponential. So I'll write it down on the screen share first, then I'll show you the conversion formula. No, sorry, write it down on the handwritten notes, I should have said. Log 10 of 1,000. There's a couple of ways you can solve this. One way is to think, this is my base, and what power do I have to raise this base to make it equal this thing? That's fundamentally what logarithms are. If you ever forget how that works, then you can just go straight to the conversion formula for exponential direct to logarithm. I'm not particularly fussed which way you want to do it. How should we proceed from this point here? How do we solve this?
Would you sub in potential values for 10 to the power of x?
Yeah, that's a brilliant way of doing it, I'd say. If you're not too convinced on exactly what it would be, then yeah, you can test some values. What would you test?
Probably 2, 3, and 4.
Yeah, 2, 3, and 4. So 10 to the power of 2, 100, 10 to the power of 3, 1,000. We already won, but just for the sake of it, 10 to the power of 4, 10,000. So we've got our match. Therefore, this should equal 3. That's about as chill as it can be, really. If you look back at the screen share, you'll notice there's a whole bunch of different ways to do it. A whole bunch of different things to try. You've got negative possibilities when you have fractions. And if you have this decimal stuff going on here, my recommendation is convert that to a fraction instead. So that like 1c, for example, if I start writing that one down, log 10 of, so 0.001 would be 1 over 1,000, and even better would be to flip any fractions into something with a negative. Well, actually, it's up to you if you want to make it negative indexed or not. Whatever makes more sense, visually speaking. Point being, whenever you have a fraction, you would test negative powers of 10 to get there, rather than positive powers of 10. Okay, that is that. Question 2 starts looking at the log laws. So what I'll do is I'll do a screenshot of those log laws, and we can at the very least talk about what's going on. The other two we didn't touch on were product law, which means addition becomes multiplication of terms, and subtraction means division of terms. There's a screenshot of that in the chat. While you have a read of that, I will write out 2a, and we'll have a think about how to solve that. All right, when you're ready, let me know how we should handle an addition of logarithms. I guess I'll remind, there is no like solve here. It's more so just hey, we have 2 logarithms, I only want 1 logarithm. How would I go about that?
Which question are we doing?
The one that I've written down. So natural log 2 plus natural log 3. How does that simplify down? If you were just to get it down a same logarithm.
Would it become natural log 6?
Yeah, natural log 6. So the law that Upraj was pointing out was product law. If you look at the screen share, whenever you have 2 logs that have the same base and they are added together, then you can replace that with a single logarithm that has the product of those 2 terms. 3 times 2, 6. Natural log of 6. Cool. That's that one. Real quick, we'll do part B just to practice the other log law, and then we'll put them together. So, in fact, I'll just make up my own one. Natural log 3 minus natural log 2. Really inventive, I know. What if it was a minus? What am I doing there?
Natural log 3/2.
Yeah, natural log 3/2. Perfect. Okay. Now for something a bit more fun, we'll put multiple log laws together. So let's go straight to H. I write that one down. I'm going to have natural log of x plus y plus natural log of x minus y, and then minus natural log x squared minus y squared. And we got close to that one, and get rid of it. Cool. So, got multiple things going on there. What might we start doing?
Would we evaluate the natural log and then put the x squared plus the x squared minus y squared in the brackets after solving the quadratic expansion?
Yeah, so you're saying to start with product law to multiply x plus y and x minus y?
Yeah.
Yeah. Okay, so it's going to give us natural log x plus y and then x minus y as a product. You're still going to have that same logarithm on the outside. Yeah, quadratic this up. Actually, yeah, we could do that. So x squared minus y squared plus xy minus xy. Okay. X squared minus y squared. And then from here, what does that now simplify down to? Natural log 1, precisely, yeah. Now, here's a interesting thing. Natural log 1, I haven't really mentioned it today yet. If you point your eyes towards the screen share, what we know is that anytime the bracket is 1, the entire logarithm becomes 0. And so the final answer for this is actually going to be 0 because we got it all the way down to natural log 1. The reason why for that is, well, all these identities can be proven by converting to exponential. Log a of 1, if it equaled something, could be converted to a to the power of y equals 1. And the only way you get that is if y equals 0. So if y equals 0, then this logarithm should equal 0. Okay, that is that. That's about as complicated as that will get. As for solving logarithms, so solving for x, let's see, what's a nice... Probably jump all the way to 4e. Why not? Let me get a new page. Okay, 4e. We've got 2 natural log of x minus natural log of x take 1 equals natural log x plus 3. Now, condensing things down, is still important, but we're now also solving for x rather than just smashing things together. So that's another thing to consider as we're solving this. But to start it off, what might we do? Got a bit of a trick to this one as well.
Would you bring the natural log x plus 3 over to the other side?
Yeah, that's one thing we could do. 2 natural log x minus natural log x minus 1 minus natural log x plus 3 equals 0. That's fine. Condensing things down is still a good idea. There is
Do we use
something.
product still?
Well, product not quite, because it's all subtraction.
The other one,
Yeah.
when they divide the two
Yeah.
things out of brackets.
So the interesting thing here is now the order of division, well, because, the order in which you do this now starts to matter. When you have this minus this is your numerator, this is your denominator. Now there is something interesting that I haven't quite mentioned, which is what do you do when you have a coefficient and you're trying to use your log laws? Because one thing you'll notice now that I pointed out especially, is every log law that I've shown, if you point your direction to the screen share, all of them, with the exception of the power law, technically, starts with a logarithm that has no coefficient on it. Now, you can handle it. You can handle it if there is a coefficient there. It's just easier to get rid of it. And the way you, quote, get rid of it is to use the power law first. So you take the coefficient and bring it in as a power to begin with. So you're going to have natural log of x squared minus natural log of x minus 1 minus natural log of x plus 3. We're about to hit time here, so I'll just sort of speed through the rest of it. But yes, the next step from here would then be doing your divisions. So x squared divided by x minus 1, and then again divide by a further x plus 3. That's all trapped in a logarithm. That equals 0. Now, the thing you do from here is convert because the x is trapped inside the logarithm, you convert to exponential, which briefly you'll have to memorize this at some point, but base of e equals 0 equals thing in brackets. E to the 0 is just 1, and now you're just solving a quadratic. X minus 1, x plus 3 equals x squared. This is just a quadratic at that point. If anyone wants to stay behind to watch me finish that quadratic, feel free. Otherwise, this logarithm is basically solved. Okay, so to finish that off, x squared, going to have minus 3, going to have plus 2x, and you bring the x squared over. Actually, it's not even a quadratic at this point now, because these cancel out. Minus 3 equals minus 2x, and then x equals 3 over 2. Do I need to explain any more of that? Easy. Alright, enjoy the rest of your day, guys.